In preparation for our closer examination of plate tectonics, we'll take a closer look at the Earth's lithosphere. The lithosphere includes the crust and the uppermost mantle, approximately 43 miles of vertical depth in association with the upper portion of the Earth itself. Through the study of earthquakes, physical geographers have been able to determine the nature of the Earth's crust and its mantle. These particular kinds of seismological studies have also told us that there are transitional zones or discontinuities which seem to separate the physical nature of each portion of the Earth's internal composition. As we take a closer look in this case, at not only the lithosphere, but what lies below it, there are two important transitions that we should discuss and take a closer look at. The deepest transition is known as the Gutenberg transition, or discontinuity. It separates the molten metallic iron outer core of the planet from the lower mantle. The region is composed chiefly of iron and magnesium-rich silicates. A second transition that is directly applicable to our definition of the lithosphere is the Moho transition. The Moho transition separates out the rigid uppermost mantle from the crust. And in this case, the crust will have two particular categories. It will be both oceanic and continental, but we'll get to this in just a moment. The Moho transition is named after a Yugoslavian seismologist who initially discovered it. It is situated really within the lower portion of the lithosphere, and it varies by location. It will also vary in terms of thickness. Generally, when we take a look at the shape of landscapes on the surface of the planet, we'll see a corresponding reflection in the transition that we call the Moho transition below. So when we take a look more closely at this discontinuity or transition important to the lithosphere, we realize that it appears ragged in nature. It will have peaks and valleys throughout. When looking more closely at the general physical features of the Earth's lithosphere, we have to engage the idea of the geologic or rock cycle. The Earth's crust is relatively thin when compared to the total mass of the planet. We still have had challenges to completely penetrate it, to drill through it. So a lot of, again, what we know about the physical makeup of this is through mathematical models, and then of course through the work of seismologists. There are two very important processes or categories of physical processes that are at work constantly within the lithosphere. One is endogenic, meaning these are internal processes building landforms, and then exogenic processes. These would be erosional processes, sometimes at the surface of the planet. They're external, wearing landforms down. So the geological cycle is very much at flux. It's a dynamic system. It's fueled by two sources of energy, the Earth's internal heat and the solar energy that we receive from the sun. These endogenic and exogenic processes are always at work, making this a very dynamic system, at least if we look at the lithosphere through a systematic lens. It is a cycle of give and take between not only these categories of processes, but also the nature of the atmosphere and the hydrosphere. In fact, if one is to step back and look at the lithosphere more holistically, we see it really existing at the interface between the Earth's atmosphere and the hydrosphere. The other thing that I mentioned earlier is that when we look at the lithosphere, it's physically made up of two major parts. We have continental crust and we have oceanic crust. Again, the crust is the uppermost layer within this lithosphere geologically. Continental crust in this case is essentially made of granite, or it is granitic. It is crystalline in nature and high in terms of silica, aluminum, potassium, calcium, and sodium. It is also very low in its overall density. If we are to juxtapose this aspect of the crust, continental, with oceanic crust, we find that oceanic crust is generally basaltic in nature, or it is composed chiefly of basalt. It is granular and very high in silica, magnesium, and iron. Oceanic crust is the more denser of the two. It's denser than continental crust. So this difference in crustal composition also becomes important as we begin to look at the lithosphere and its many landscapes across the planet. This diagram gives us a real good resource for understanding, even visually, how this geological cycle as a system works and how it fits into our understanding of the lithosphere. When we talk about this interactive cycle, we not only see the byproduct, which are the major types of rocks that make up our landscapes, but we also understand something more deeply regarding the tectonic cycle. Crustal plates and their movement, in a sense, bring heat into this geological system from below. It also brings or transports through things like seafloor spreading, subduction, and crust formation material into the system. The materials and the heat from below the crust, in a sense, represent a kind of systematic input, as does the solar energy from, again, entering the system from above. So materials, in a sense, are brought to the Earth's surface, while materials are also being recycled in this kind of circular process. We see the deformation and the movement of the crust occurring not only in this image, but throughout the lithosphere itself. This particular image is great because it's giving you insight into how the hydrosphere and the hydrologic cycle works in tandem with the tectonic cycle. The depiction is also a good example of subduction and seafloor spreading, two things that we will touch upon in our tectonics unit. However, you can see how these particular kinds of crustal movements and really the composition of crustal bodies themselves, whether they are oceanic or continental in nature, are very important for creating landforms and for recycling materials in this geological cycle. Take a moment now to study this diagram and compare it to not only your readings, but some of the things that we've talked about already in this lecture. Along the bottom of the diagram, you will see a symbol system and a system, almost a kind of a diagrammatic system for understanding how the various processes are at work within the geological cycle and how they ultimately contribute to the formation and deformation of, in this case, material within the lithosphere. In the picture itself, just above that lower portion, you will see, in this case, many of the terms that you're reading about and many of the terms that we'll be discussing again in this lecture and the next lecture. It will also give you a sense of what the lithosphere is. It will give you a sense of, in this case, continental and oceanic crust. And then, as I said earlier, the processes that are at work and the types of rock and rock material that are being formed as we have an interaction between things like the hydrologic cycle and the tectonic cycle. Now let's take a look at the materials themselves. We will again focus on the rock cycle or geological cycle and its overall composition. In this case, one of the most important concepts that we need to keep in mind is that there are building blocks. There are really only 8 natural elements that compose nearly all of the Earth's crust. Oxygen and silicon, for example, comprise approximately 74 or more percent of the crust. Oxygen is the most reactive gas in the lower atmosphere, and so it is something that, in terms of a earthly element, will connect the geochemistry of the lower atmosphere with, in this case, the geology below. The low density of silicon and aluminum account for their status as a kind of runner-up to oxygen and silica. Silicon and aluminum are less dense substances, and they readily migrate through and to the Earth's surface. So if we are to list these 8 elements, at least these 8 major elements out, in terms of their abundance, we would of course start with things like oxygen and silicon. From there we would move to aluminum and iron. We would then move to calcium, sodium, magnesium, and potassium. The final 2 elements which make up that small percentage of missing material, this would be the 1%ers in a sense when we combine them, would be titanium and hydrogen. Now, what's great about this is we have 10 complete elements that make up everything in terms of our lithosphere, 8 of which are the major players. And the combinations of these both 8 and 10 elements make up our earthly minerals. So a mineral is an inorganic or non-living natural compound that has a specific chemical formula to it and possesses a specific or a unique crystalline structure. The unique combination of elements that make up each mineral type and its crystal structure, in a sense, give it its characteristics of things like hardness, color, and physical density. Mineralogy, then, is the study of the composition, properties, and the classification of mineral types. If we take a look, for example, at a common mineral like quartz, chemically it's known as silicon dioxide. This is a very distinct six-sided crystalline structure. It is important, it's a mineral with and it's very common rather, in terms of rock formations. So quartz, given its chemical nature, being composed in this case of silicon and oxygen, it becomes a very important rock forming mineral. It is also part of a very large family of minerals, in this case the silicates. Today, mineralogists recognize over 4,200 different mineralogical combinations, and these important combinations are responsible for all of the landscapes that we see on the modern planet. Of the 4,200 mineralogical combinations, 30 minerals are recognized to be the most important in terms of the rock forming processes. We will take a step back and look at the three major rock forming families, or three major or most widespread mineralogical families. The first family that you see listed here is the silicate group. And I mentioned silicates in relation to quartz, but they are probably the most widespread of the three. The reason for this is because, as I said before, silicon and oxygen are very, very common in terms of the elements within the lithosphere. Also, silicon and oxygen, by their nature, chemically love to combine with one another and with other elements and compounds. Along with quartz, things like chert and feldspar are very good examples of silicates. In terms of soils, which we'll be looking at in our next lecture, the minerals that are part of clays or clay-rich soil horizons are also going to be a good representative or good representatives of the silicate family. Our second mineral group or family is the oxides. This is a group which includes mineral combinations where oxygen is actively bonding with metallic elements. A very good example for the oxide group would be hematite. This is a very common, very red appearing kind of mineral. It is a combination of iron and oxygen. So we recognize the presence of two iron molecules and three oxygen molecules that have, in a sense, been combined into this compound, or at least the chemical structure of the compound. Okay, then our last group would be the carbonate group. This features carbon in combination with oxygen and other elements such as calcium, magnesium, and potassium. At least those are the heavy hitters. The calcite, or calcite in a sense, as a mineral represents, or is a good representative of this particular group and its common bonds, in this case between oxygen, carbon, and in this case calcium. So we have three major mineralogical families. What do they produce? Well, simple answer, they produce rock. So what is a rock? Well, let's give you a definition for that. So a rock in this case, or at least for this class, is an assemblage of minerals that are bound together. A rock can be a single mineral, or it can be undifferentiated, or it can be a solid organic material. If we take a look at something like granite, here we have a rock that contains three minerals. Or if we look at a rock that has, again, a kind of a single mineralogical quality to it in terms of its mass, something like rock salt would be a very good example of that. Or a rock, as I said, can be an undifferentiated material, such as a non-crystalline volcanic glass or volcanic rock, in this case, such as obsidian. Or it can be a solid organic material like coal. So now we'll take a look at the classifications of rocks, and we'll recognize in this case three main types of rocks. And the type of rock that we'll be looking at in these kind of three examples are all defined in terms of how they are produced or the mode of their production within the geological cycle. The first type that we will be looking at and that you'll be reading about is igneous rock. So defined in this case as rocks that solidify and crystallize from a molten or liquefied state. Familiar examples of igneous rocks would be granite, basalt, and rhyolite. Igneous rock forms from then magma. So magma is the term that we will apply to this molten rock that is generally existing beneath the surface of the planet. Magma, as I said, is fluid. It's also highly gaseous and generally under tremendous pressure. As it moves, it will either intrude into crustal rocks where it cools and hardens, or it will extrude onto the surface of the planet and it will become another term, in this case, extruded magma being lava. Now, what's interesting about these two expressions of what the fluid state of unformed igneous rock is doing is that the cooling history of an igneous rock will also be a part of how it is classified. The speed of which a liquefied material prior to becoming igneous rock is cooled and solidified determines its crystalline structure. It will also determine many of its physical properties. You will have igneous rocks that are categorized as slow cooling in their formative process. These will generally be coarse grained, similar to the kind that we see here, this rhyolitic granitic material in this photo. It will also sometimes be cooling at a very fast rate, and that's where we will get this unconsolidated kind of volcanic glass, such as obsidian forming. I should say undifferentiated as opposed to unconsolidated. A little bit different there. Igneous rocks comprise approximately 90% of the Earth's crust, although they are often covered by other layers of rock. More often than not, sedimentary rocks will cover up igneous layers. Common sedimentary rocks that will interact with igneous layers will be things like sandstone, shale, or limestone. Now, based upon where an igneous rock forms, we have another subcategory of details that we can add to it in terms of how we are classifying it and categorizing it. There is an area where we have intrusive igneous rocks forming. An intrusive igneous rock cools at a very slow rate inside the crust that it forms within. A pluton, for example, is a good example, or it is a term also that we apply to these intrusive igneous rock types. Plutons will often provide us with the foundation for many of our mountain ranges. The term Pluton is associated with the Roman god of the underworld, Pluto. Now, there are different types or kinds of plutons or igneous rock that is, again, intruding into rock layers and then forming. The largest pluton is known as a batholith. This is defined as an irregular shaped mass with a surface area that is greater than 40 miles. Batholiths would be the mass associated with many of our largest mountain ranges, as I mentioned. Smaller plutons exist, though. These will include magma conduits in ancient volcanoes that again have cooled and hardened, and they will often be expressed in a parallel fashion. These smaller plutons that have this parallel nature to them will be referred to often as sills. When a pluton crosses layers of rock, or as it kind of invades rock layers, it will be categorized or classified as a dike. And then magma, that as it is highly pressurized below ground, bulges and intrudes into layers, creating envelopes of new rock, will often be called a laccolith. It's a type of sill. Now, another major category of igneous rock types are extrusive in nature, meaning that as these igneous rock layers form, we have volcanic action. Volcanic eruptions and the flows associated with them will produce extrusive igneous rock. A common type of extrusive igneous rock is basalt. So a lot of the extrusive igneous rock formation processes that we see on the planet today are generally associated with our oceans. These rock types will have smaller grains to them, or their crystalline structure will be much smaller as they are cooling at a very rapid rate. As you can see in this image here, we have a crystalline structure that is associated with basalt. So there you have it. You have an intrusive group and you have an extrusive group. Now, there are other ways that we can classify and categorize igneous rocks. One of the additional methods we can use is to look at their composition and their texture. So that's what we'll look at next. So in terms of composition and texture, we have categories such as felsic that we apply to igneous rocks. So a felsic igneous rock, or when we use the term felsic, we are describing something that's derived from both the composition and of course the name of its chemical makeup. So we have generally a lot of feldspars expressed in these rocks, and we also have a lot of rocks that fit into that silicate group. Felsic minerals will also generally express high amounts of silica, aluminum, potassium, and sodium. They will have very low melting points, and the rocks formed from felsic minerals will be generally lighter in color, and they will be less dense than the other group, the mafic group. So this would include granites, rhyolite, and volcanic rocks such as pumice. The other igneous group that we recognize in terms of composition and texture is the mafic group. This term is derived from both the composition and the name of common minerals within mafic igneous rocks, such as magnesium and a ferric element such as iron. Unlike felsic rock, mafic minerals are low in silica, high in magnesium, and of course iron, and they also have very high melting points. The rocks formed from mafic minerals are generally darker in color and have a greater density than the felsic minerals. This would include things like basalt, which is finely grained, and it would include another common type, which is gabbro, which we see depicted here in this slide. Gabbro is slow cooling. It will have a coarser appearance to it, and you can see this in the image. You may wish to pause the lecture at this point and take a very close look at this chart. It will give you a sense of how each of these distinctions organize the different kinds of rocks that we interact with when we're looking at the igneous type. It will also give you some of the names of common mineral families and the rocks associated with them. Another major type of rock beyond now igneous would be sedimentary in nature. Sedimentary rock is very much a product of solar energy and the water that drives processes such as sedimentation and lithification. Water in this case physically moves material in this process. It will move it systematically from areas of high energy to areas of low energy and deposition. Another important aspect of the formative processes associated with sedimentary rock is that you will have existing rock that is being broken down by processes generally exogenic, such as weathering. It will be then picked up and moved by transportation or by a process of water transport, and then of course it is still part of that erosional process, where it is then deposited along a river or a beach or an ocean site. The burial of this material then begins to solidify it. It begins the process of lithification. which is synonymous with not only sedimentation but also the cementation of particles within the developing body of rock. So in terms of a definition for lithification, we would use the following. Lithification is the formation of sedimentary rock via or by the cementation, compaction, and hardening of sediments. So it's the formation of sedimentary rock via the cementation, compaction, and hardening of sediments. The most common weathered materials that we see being, in a sense, gathered up into this process, these would be the building blocks of sedimentary rock, are things like quartz or feldspar or clay. These materials are, as I said before, generally moved from a place of high energy where they're being eroded or weathered, or at least the material that they are originally part of is being weathered, and then they are being transported. They're being transported generally to areas of low energy, these sites where deposition occurs. Common sedimentary rocks include things like sandstone, which is cemented sand particles, or shale, which is mud that has become compacted and cemented into rock, or limestone, which is a common component in many of the bedrock outcroppings of the Midwest. This would be organic matter that has become cemented, or calcium carbonate that has been precipitated out of water and then again forming into some sort of, in this case, sedimentary rock like limestone. When you hear me use the term precipitation in this case, or when you are, of course, reading a section on geology that describes a material being precipitated out of maybe a watery environment, basically this is a situation where a chemical compound is being solidified, and it begins, in a sense, in a state of solution. So it's being carried in solution, and then as that solution diminishes, as it evaporates, for example, what is left behind will be a precipitate. So many sedimentary rocks are also connected to this chemical process. And then a kind of a final common type of sedimentary rock would be something like coal. Coal is a sedimentary rock that represents ancient compacted plant matter. Now, in terms of how we further classify and categorize this rock type, in this case sedimentary rock, we really use only one major strategy, which is or relates to how the rock is formed and its composition. So we recognize clastic and non-clastic types of sedimentary rock. Clastic sedimentary rock is generally weathered, fragmented rock that is worn down and transported, but the fragments or the clasts remain. If you think about something like sandstone, the feel of the sandstone or the appearance of sandstone still reflects the idea that we have sand particles that are being compacted and cemented together. Now, not all clasts are visible. Many of these have to be understood under magnification. This would include other kinds of clastic rock types such as siltstone or mudstone. There is another class or category within sedimentary rock known as non-clastic. Non-clastic sedimentary rock would be chemical sedimentary rock, or it is rock material that is not formed from physical pieces of broken rock. Instead, they are formed from dissolved minerals that are transported rather in solution and then chemically precipitated from that solution. Environmental qualities, or the environmental qualities of a site where non-clastic sedimentary rock forms, becomes very, very important. They play an important role not only in how the rock forms, but then how we study and analyze it, how we further classify it. Things like hot springs, for example, can act as a catalyst for different kinds of chemical reactions as material precipitates. Um, and we see in hot spring environments the intrusion of and reaction of things like oxygen. Um, we'll see a change in color usually associated with these particular types of rock. And this process of lithification, where we have non-clastic sedimentary rock forming in an environment that is associated with heat and hot water, in this case, it's understood as hydrothermal lithification. So that's just one example of how the environment where sedimentary rock is forming, especially sedimentary rock that is non-clastic in nature, how that is very much a part of how we observe it, how we analyze it, how we know it. The last major category for rock types would be metamorphic rock. Metamorphic rocks generally are either sedimentary or igneous rocks that are transformed into a metamorphic rock type. Now, in terms of this transformative process, usually things like pressure and temperature are major players. As a result, we find that metamorphic rocks are generally more compact than the original rock material that they are being modified from. Compression and the heating of rock occurs when rocks such as igneous rocks become compressed during collisions between slabs of the Earth's crust. Sometimes rock simply is crushed under the great weight of the layers of crustal rock above it. Other times, seismic activities can also stress rock, or the rock itself can be stressed by the interaction of tectonic plates. Whatever the case might be, the theme here is that we have a parent material that is being transformed. There are a variety of ways and of physical environments in which metamorphic rock layers will form. One in particular is known as regional metamorphism. This is when sedimentary rock, in a sense, overlying the material, is creating a significant amount of pressure weight that will ultimately lower the stratigraphic layers and compress them even further, thereby transforming them even on a chemical level. Regional metamorphism, in a sense, is can be rather large scale. We see regional metamorphic processes at work in many of our earthly mountain chains. Another example of a formative process known as contact metamorphism can be witnessed internally in mountain chains. In this case, we see it in many of our granitic mountains throughout the globe. Deposits here of sedimentary strata will be cooked because of the close presence of intrusive magma and their contact with this intrusive material, both in terms of physical contact, but then also the intensive increase in temperature as that intruding magma gets closer and closer to those layers will result in the metamorphic process, in this case contact metamorphism. As a result, there are two classes of metamorphic rock types, foliated and non-foliated. And generally, when we describe something as being foliated or non-foliated, we're describing the texture of the rock material. Foliated metamorphic rocks are rocks in which minerals are being transformed into wavy patterns in terms of how we view them. The parent rock in this case may not be uniform in its texture and composition, and then it results in these very dramatic kinds of waved visible forms. A rock like gneiss, 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 is an example of a foliated metamorphic rock. A non-foliated metamorphic rock is a rock in which the parent material is more homogeneous in its overall structure. It's more evenly mixed. It's less coarse in a sense. This would be, or would examples of this would include things like marble or quartzite. Marble and quartzite are examples again of non-foliated metamorphic rock. And the parent material, the material that they are initially drawn from, is more evenly mixed in terms of its crystalline structure. So take a look for a moment, review the small table that I have embedded in this slide. Compare, in this case, the kinds of parent materials that you see listed on the left-hand side of the image to what metamorphic results we see on the right side. So what you will find when you look more closely at this table is that a parent rock material like limestone or dolomite, because of its uniform nature, will result in a more uniform, non-foliated metamorphic rock like marble. When you compare this to the distinctly layered parent material like shale, again, layer after layer of um, sediments that have been compacted and cemented together, and these sediments generally are clay minerals, what you will find is it will result in a foliated rock such as slate.